In this video, we are going to return to our princesses once again because we would like to study a new method for writing functions within permutation groups. So we're going to get some context for why this particular method of writing functions in this way might be important. I'd love to have my real princesses back with me, but this is really an example best visualized with the princesses on the screen, given that we can't do this in real life with a real-life volunteer. So let's imagine that we have 5 of our princesses on the screen. Because these are my digital renderings of the princesses and not very good Disney renderings of the princesses, I'd like to introduce that we have Ariel, Belle, Tiana, Cinderella, and Rapunzel with us. And the goal I have in mind for these princesses is for them each to be in their own original dresses, which I have pictured right here. But we will imagine that these princesses are not currently in this state. They are currently wearing each other's dresses in a very methodical way. Namely, you'll notice that Rapunzel's dress is over here on Cinderella. Cinderella's dress is over here on Tiana. Tiana's dress is here on Belle. Belle's dress is on Ariel, and last but not least, Ariel's dress is right over here on Rapunzel. So our goal is to get to here, and currently every princess has their dress shifted 1 to the left. So if we had our actual princess clip dolls, and I had a volunteer who was going to come to fix the princesses clip dolls for me, that volunteer would probably start over here on the left and work their way to the right, taking off Belle's dress, which is currently on Princess Ariel, in order to give it to her. So the first move would typically be to take the dresses off of Ariel and Belle in order to give the dress that Ariel was currently wearing to Belle. So she needs to take the dress off to give it. She needs to take her dress off to receive that dress. And then once the student goes ahead and takes those 2 dresses off, my first reaction is to immediately yell at said student and say, "What are you doing? Why are you putting these princesses on display to everyone? This is so embarrassing. Have you no shame? Quick, quick, quick! Put some clothes on these princesses." And so the student does the only natural thing in that situation, which is to put Belle's dress on her and take the only other remaining dress, the dress that Belle was previously wearing, and put it on Ariel, so I'll stop screaming at them to clothe the princesses. And now look, all the princesses are happy because everyone is decent. Now just an update on the state of the dresses. Belle is wearing her correct dress. So we've made progress in working towards our goal. These dresses are entirely unaffected by what has just happened because they weren't involved in the slightest. But Belle and Ariel have swapped dresses due to the necessity to put something, anything, the only thing available, back on Princess Ariel. Now, what would our next step be moving in this way, taking off the minimal number of dresses and making a change, and then forcing everyone to stay clothed? The natural next step is to look at the fact that Ariel is now wearing Tiana's dress. So I can do a similar thing by taking off their dresses and exchanging, so that Tiana now has her correct dress, and Ariel is wearing the only dress that was left, Cinderella's dress, the dress previously worn by Tiana. And we can continue in this way, swapping Cinderella and Ariel's dresses. And last but not least, we'll end up with Ariel and Rapunzel needing to switch dresses one more time. All the princesses have their right dresses on, and they are happy. Now let's take the princesses example and let's move that back to just the much more boring example where we have this correspondence between princesses and numbers, and let's just think about shuffling the numbers 1, 2, 3, 4, 5 forward by 1, where 1 maps to 2, 2 maps to 3, 3 maps to 4, 4 maps to 5, and last but not least, 5 wraps back around to number 1. What we were doing with the princesses is somehow decomposing this particular cycle, which is an example of a permutation, as a product, and I've put the word products in quotation because really what I mean is as a combination of elements within this group that happen to be two cycles or transpositions. And what those are just maps that switch exactly to numbers. If you're thinking about typing in something like credit card numbers, a very common user error is for the user to look at two digits and just interchange them. It's called a transposition. And that's the goal of what we're doing today. Our goal is to learn how to take an arbitrary permutation and write it as this so-called product of transpositions or interchangements of two things. So what we did in the previous example with the princesses is we picked two princesses, 1 and 2, to switch their values. And so that's the whole map that we should have right here, is just a switching or a transposition of two values. At this point, when we look at this map and follow through like we would for composition, the 1 value is being mapped to the 2. And so from here on out, we never want the 2 value to go anywhere else because it's exactly where it belongs. In the end, we want 1 to map to 2, and the easiest way to do that after this first switch is to just never change that value of 2, like that. Now, we haven't touched the 3, 4, and 5, so let's not think about them quite yet, but know that where the 2 was, the 2 has now been mapped to 1. And ultimately, we want the 2 to map to the 3 position. So the 2 maps to the 1. The natural next step is to have that 1 map to 3. And because this map needs to be a transposition, that means the 3 value needs to map to the number 1. At this point, the 2 does map to the 3, and we never want the 3 to change again. The easiest way to accomplish this is to have 3 never change again at all. And we keep on going in this way. Now, the 3 maps to the 3 maps to the 1. Ultimately, the 3 should go to the 4, so we'll make that exchange right here. And after we've fixed it so that the 3 does map to the 4, we'll keep that value constant. And in this last place, we now have everyone going where they want, except that we want the 5 value to map to 1. 5 hasn't been touched in any of these transpositions, so if the 5 is ultimately to go to 1, it must do so here, and the 1 must map to the 5, and it's this particular combination of transpositions that's going to give us the cycle 1, 2, 3, 4, 5. Now there are lots of questions that might come to mind as we describe this process. The first of which is, how do we formalize in general what was done previously with the princesses to any number of princesses? How do I take an arbitrary M cycle and decompose it in this way as a so-called product of transpositions? And the next question is, how many transpositions are required? After thinking about that, you'll want to think about the next question. Once I feel like I know I can do a thing, is that method that I've employed the only method of getting that to work? If so, how would I prove it? And if not, can I come up with an alternate example? So that's the next thing I'd like you to think about. Once I feel like I have a general method for taking a cycle and decomposing it as a product of transpositions, then is my method unique? And third of all, what about fixed points? We want to think generally about how we would take any old function in the world and write it as a product of transpositions. The first thought is, I'll do that cycle by cycle. However, there are some numbers that are called fixed points in a function that aren't affected by the function. Am I able to write a fixed point as a product of transpositions as well? And if so, how would I do that? So these are good questions to end with, and we can start our next video with revealing some possible answers.